In the previous session, we had introduced missing data. So, we had known what is the scenario that rises to missing data and what are the methods that we can adopt in case of missing data. So, mostly there are two groups of method that can be implemented. One is the imputation based methods and one is the model based methods. So, from this session onwards, we would emphasize on the model based methods or the likelihood based methods for missing data, and once we are through with the model based methods, we would be dealing with or learning the imputation based methods for missing data. So, here we would start with how can we make a model for missing data only based on the complete data, and how can we use likelihood based methods to answer questions related to our data set which has missing as well as non-missing data. Particularly in this session, we would be seeing that the different types of missingness, how they are in presence of a model based missing data analysis. So, that means how are we going to define MCAR and MAR in context to a model based missing data formulation. So, the objectives of this session is formulation of likelihood for missing data, defining missing data indicators, and revisiting the missing data mechanisms and implementing some of our theoreticals using R. So, consider Y to be the observation vector n dimensional in nature. So, then I can split Y into two sub vectors. One is Y observed and Y miss, where Y observed is the observed values of Y and Y miss is the missing values. Now, then the density f y given theta, where theta is the set of parameters, is written as or can be written as f y observed comma y miss given theta. So, that is the probability or density or the joint density of y observed and y miss. Now, I can then integrate out over y miss to get the marginal density of y observed, that is f of y observed given theta is nothing but integral of f y observed y miss given theta with respect to y miss. So, ignoring the missing data mechanism, the likelihood for the parameter vector theta is L, theta given y observed, and this is proportional to f of y observed given theta. Now, inference of theta is now based on L theta given y observed. Now, to perform the inference, we need to define what is called a missing data indicator. Now, the response indicator R is defined in such a way that R is equal to R1, R2, Rn, where Ri is equal to 1 if yi is observed and 0 if yi is missing. Then R can be treated as a random variable. The joint distribution of R and y is the product of the distribution of y and the conditional distribution of R given y. So, f of y r given theta psi, and coming to what is psi in a moment, is f of y given theta into f of r given y and psi, where f of r given y and psi is the conditional distribution of r given y and psi is the unknown parameter on which the conditional distribution is based on. Usually, we assume that psi does not involve theta, that is psi is independent of theta. So the actual observation is now y is y observed and r. So f of y observed r conditional on theta and psi is f of y observed y miss given theta into f of r y observed y miss given psi dy miss. So that means we are from the joint distribution of y observed y miss and r, we are marginalizing out the joint distribution of y observed and r. So here likelihood of theta and psi is like proportional to y observed r, density of y observed r given theta psi. So that's on this. Now what happens? Now how are we going to define the missing data mechanisms in this context? Note that f of r conditional on y and psi is equal to f of r given psi. Now if we assume this implies r and psi are independent, and using this in the above, what we can get, f of y observed r given theta psi is equal to f of r given psi. It is free of y and integral f of y given theta, and here this y means the complete observations, all observations. So that is y observed y miss dy miss. Now what happens? Let us take an example. Let y be a p cross 1 vector and let y observed be the first n cross 1 observation. So the first n observations are observed and the remaining p minus n observations are not observed, and assume that y follows np mu sigma. Then we know that y observed follows nn. So if the entire y follows a multivariate p dimensional multivariate normal, then the y observed follows a n dimensional multivariate normal with mu observed and sigma observed, where mu observed and sigma observed are appropriate submatrices of mu and sigma. So under M-car what happens? F of y observed r given mu sigma and psi is nothing but f of r given psi and then integral of f y given mu sigma into dy miss. Now f of r given psi, this is equal to f of r given psi into f of y observed given mu observed sigma observed, which means that f of y observed r given mu sigma and psi is proportional to f of y observed given mu observed and sigma observed. So under M-car, the maximum of f of y observed r over mu sigma and psi is nothing but maximum over mu sigma f of y observed, mu observed and sigma observed. So whether we are including the missing or not doesn't really matter, because the maximum is over the same over the only the observed. So that means under M-car it is equivalent to throw away the missing and use the complete case analysis. Then comes missing at random. Now what happens at missing at random? F of r given y and psi is f of r given y observed and psi, meaning that the missing depends on y observed. And if we do the same procedure, it comes down that f of y observed r given theta and psi is integral of f of y observed y miss given theta into f of r given y observed psi dy miss. So that means it is the integration over the marginals, the joint is integrated with respect to y miss, and then that comes to f of r given y observed. Note that in M-car this y observed was not there, so it was r conditional on psi only, but here it is r conditional on y observed and psi. So, for our example, this would become f of y observed r given theta psi is f of r given y observed psi into f of y observed given mu observed sigma observed. Now, non-ignorable missingness, f of r given y psi depends on y miss as well as y observed. So, here we cannot easily integrate over y miss and come to such simple conclusions. So, as an illustration, we are showing the example 5.4 of missing data analysis by Little and Rubin. So, here let us assume yi follows exponential theta, I is equal to 1 to p, and assume that the first n is observed and the remaining n minus p is missing, and the task in our hand is to estimate the parameter theta. So, f of y given theta is 1 by theta to the power n exp minus I equal to 1 to p yi by theta, that is the standard likelihood for the first p observations for an exponential distribution, or the p observations for an exponential distribution, and here it is theta to the power n, because the remaining does not have any contribution, and f of y observed given theta is 1 by theta to the power n exp, and here it is exactly the same, the only difference is that for the first it is summation up to p, for the second it is summation up to n, and we define r equal to r1 to rn, which is like first n ones and remaining p minus n zeros. Define psi is equal to probability each unit is observed. So, then f of r given y and psi follows that the ith unit is observed follows a Bernoulli distribution with parameter psi, which is equal to like psi to the power n into 1 minus psi whole to the power p minus n. Now, f of y observed r given theta psi, it comes out to be psi n 1 minus psi to the power p minus n. So, that is the missing data mechanism likelihood, as well as theta to the power minus n exp of minus I equal to 1 to n yi by theta. So, that is the observed data likelihood or observed data density. And then I can take log f, which is the standard which comes to this, and then derivative of log f equal to 0, and we find the MLE of theta hat is nothing but the observed mean. Suppose instead that the incomplete data is censored at some censoring point C. So, here we cannot ignore, or here the missingness is not completely at random, but is dependent on the censoring point C. So, if the observation is more than the censoring point C, it is missing, else it is not missing. So, here f of r given conditional on y and psi comes out to be I equal to 1 to p f of ri given yi psi. But here f of ri given yi psi is 1 if yi is less than c and 0 if yi is greater than c. So, on computation we get f of y observed r conditional on theta comes out to be theta to the power minus n exponential of minus yi by theta sum I equal to 1 to n and exponential of minus p minus n by theta multiplied by c. So, I can take the log likelihood or the likelihood which is the same as above, and the log likelihood is minus n log theta minus summation yi by theta minus p minus n by theta into c. And from there I get a estimate of theta hat, which is basically the average of the observed plus the censoring value into p minus n by n. Now, we perform the same task in R as an illustration. So, what do we do is, first we fix a seed so that at every repetition we get the same result, and this seed can be anything, and then we generate 1000 exponential random variables from theta 2. So, ideally the estimate of theta should come around 2, and here because r generates in terms of 1 by theta. So, basically the theta value that we are looking for is 1 by mean of y, that is the estimate, and that estimate comes out to be theta. Now, suppose we forcefully introduce a missing data mechanism, and how do we introduce a missing data mechanism? By choosing a position randomly where this would the values would be missing. So, we do it using a binomial function. So, we generate 1000 random values from R binomium or R binom, or that is the binomial random variables or yeah. So, we have random samples from a binomial distribution, and then what we do is, for the positions where the binomial distribution or the random values are 1, we replace it by NA, and then we find based on, so we have observed as well as unobserved values, which comes out by summary y1. So, if I give summary y1, what we would get is something like this. So, out of the 1000 we have 101 NAs, and just we ignore the NAs and compute the mean and take a reciprocal of it, and that becomes my theta missing completely at random estimate, and that estimate comes out to be 2.0503, right. So, it is round about 2 only. Now, what we do is we impose the censoring scheme by censoring if the value has crossed the 90% quantile, which comes out to be 1.17, and here we first calculate theta m ka, and that comes out to be 2.7412, while if we use missing at random and use the formula and find theta missing at random, we see that value comes out to be 2.045. So, that is pretty close to the true value. So, while in situations where it is missing at random, using missing completely at random might not yield a very good or very reliable result. So, in this session we have learned, or we have just introduced ourselves to the likelihood based procedures for dealing with missing data. In the next session we shall be dealing more on this likelihood based procedures for missing data and do some complete case analysis as well as available case analysis and see what are the results.